An elliptical galaxy is a type of galaxy having an approximately ellipsoidal shape and a smooth, nearly featureless brightness profile. Unlike flat spiral galaxies with organization and structure, they are more three-dimensional, without much structure, and their stars are in somewhat random orbits around the center. They are one of the three main classes of galaxy originally described by Edwin Hubble in his 1936 work The Realm of the Nebulae, along with spiral and lenticular galaxies. They range in shape from nearly spherical to highly flat and in size from tens of millions to over 1 trillion stars. Originally, Edwin Hubble thought that elliptical galaxies may evolve into spiral galaxies, which later turned out to be false. Stars found inside of elliptical galaxies are very much older than stars found in spiral galaxies. Most elliptical galaxies are composed of older, low-mass stars, with a sparse interstellar medium and minimal star formation activity, and they tend to be surrounded by large numbers of globular clusters. Elliptical galaxies are believed to make up approximately 10–15% of galaxies in the Virgo supercluster, and they are not the dominant type of galaxy in the universe overall. They are preferentially found close to the centers of galaxy clusters. Elliptical galaxies are also called early-type galaxies, due to their location in the Hubble sequence, and are found to be less common in the early universe. General characteristics. Elliptical galaxies are characterized by several properties that make them distinct from other classes of galaxy. They are spherical or ovoid masses of stars, starved of star-making gases. The smallest known elliptical galaxy is about 1/10 the size of the Milky Way. The motion of stars in elliptical galaxies is predominantly radial, unlike the disks of spiral galaxies, which are dominated by rotation. Furthermore, there is very little interstellar matter, which results in low rates of star formation, few open star clusters, and few young stars. Rather, elliptical galaxies are dominated by old stellar populations, giving them red colors. Large elliptical galaxies typically have an extensive system of globular clusters. The dynamical properties of elliptical galaxies and the bulges of disk galaxies are similar, suggesting that they are formed by the same physical processes, although this remains controversial. The luminosity profiles of both elliptical galaxies and bulges are well fit by Circ's law. Elliptical galaxies are preferentially found in galaxy clusters and in compact groups of galaxies. Star formation. The traditional portrait of elliptical galaxies paints them as galaxies where star formation finished after an initial burst at high redshift, leaving them to shine with only their aging stars. Elliptical galaxies typically appear yellow-red, which is in contrast to the distinct blue tinge of most spiral galaxies. In spirals, this blue color emanates largely from the young, hot stars in their spiral arms. Very little star formation is thought to occur in elliptical galaxies, because of their lack of gas compared to spiral or irregular galaxies. However, in recent years, evidence has shown that a reasonable proportion of these galaxies have residual gas reservoirs and low-level star formation. Researchers with the Herschel Space Observatory have speculated that the central black holes in elliptical keep the gas from cooling enough for star formation. Sizes and shapes. Elliptical galaxies vary greatly in both size and mass, from as little as 1/10 of a kilopasc to over 100 kilopascs, and from 107 to nearly 1013 solar masses. This range is much broader for this galaxy type than for any other. The smallest, the dwarf elliptical galaxies, may be no larger than a typical globular cluster, but contain a considerable amount of dark matter not present in clusters. Most of these small galaxies may not be related to other ellipticals. The Hubble classification of elliptical galaxies contains an integer that describes how elongated the galaxy image is. The classification is determined by the ratio of the major to the minor axis of the galaxy's isophotes. Thus, for a spherical galaxy with A equal to B, the number is 0, and the Hubble type is EO. The limit is about E7, which is believed to be due to a bending instability that causes flatter galaxies to puff up. The most common shape is close to E3. Hubble recognized that his shape classification depends both on the intrinsic shape of the galaxy, as well as the angle with which the galaxy is observed. Hence, Some galaxies with Hubble type EO are actually elongated. There are two physical types of ellipticals. The boxy giant ellipticals, whose shapes result from random motion which is greater in some directions than in others, and the disky normal and low luminosity ellipticals, which have nearly isotropic random velocities but are flattened due to rotation. Dwarf elliptical galaxies have properties that are intermediate between those of regular elliptical galaxies and globular clusters. Dwarf spheroidal galaxies appear to be a distinct class. Their properties are more similar to those of irregulars and late spiral-type galaxies. At the large end of the elliptical spectrum, there is further division, beyond Hubble classification. Beyond GE giant ellipticals, lies D galaxies and CD galaxies. These are similar to their smaller brethren, but more diffuse, with larger halos. Some even appear more akin to lenticular galaxies. Evolution. Current thinking is that most if not all elliptical galaxies may be the result of a long process where two or more galaxies of comparable mass, of any type, collide and merge. Such major galactic mergers are thought to have been common at early times, but may carry on more infrequently today. Minor galactic mergers involve two galaxies of very different masses, and are not limited to giant ellipticals. For example, our own Milky Way galaxy is known to be consuming a couple of small galaxies right now. The Milky Way galaxy is also, depending upon an unknown tangential component, on a collision course in for euro 5 billion years with the Andromeda galaxy. It has been theorized that an elliptical galaxy will result from a merger of the two spirals. Every massive elliptical galaxy is believed to contain a supermassive black hole at its center. The mass of the black hole is tightly correlated with the mass of the galaxy, via the μ/σ relation. It is believed that black holes may play an important role in limiting the growth of elliptical galaxies in the early universe by inhibiting star formation. Examples: M32, M49, M59, M60, M87, M89, M105, IC1101, one of the largest galaxies in the observable universe. Matthew 1, the closest giant elliptical galaxy. Centaurus a radio galaxy, elliptical lenticular disputed. See also, firehose instability, galaxy color magnitude diagram, galaxy morphological classification, Hubble sequence, lenticular galaxy, μ/σ relation, OC cover merit model, Cirsic profile. Further reading: Ho, Herjan. Van den Bosch, Frank. White, Simon, Galaxy Formation and Evolution, Cambridge University Press, ISBN A978-0521857932-. References. External links: Elliptical Galaxies, SEDS Messier pages, Elliptical Galaxies.